Hello everyone, my name is Harun ÇELİK. I'm working as an assistant professor in the astronautical engineering at Erciyes University. I will talk on the learning capacity of air vehicle flight controller. Can an air vehicle learn to fly? Can recent technologies handle the nonlinear complex dynamics of flight for learning to fly? Is it possible to design an intelligent flight controller which is able to learn to fly? Let me make several statements about this title. Flight controllers can be classified into two categories. With this separation, we can call the first category as classical control, under which lead lag and P.I.D. control can be listed. These are linear control methods, and the P.I.D. is the most common control method using in industry and also in aviation too. The other category can be called modern control. A dozen of methods can be listed under modern control. Robust control, adaptive control, optimal control. And for our studies, as our purpose is to examine the capacity of an air vehicle to learn to fly, the most convenient one is intelligent control. Based on artificial intelligence and in contrast to other modern nonlinear controllers, intelligent control is not heavily relied on dynamic models of air vehicle during real-life flights. It can eliminate the dependence of air vehicle model that is prone to the accuracy of the trim information. Intelligent control can provide model-free control by using machine learning algorithms. Machine learning. As a machine, we have aerial vehicle. For learning, in fact, a significant portion of learning occurs through engagement with the environment, occurs through observation of natural phenomena. Learning from nature has been a fundamental source of inspiration for many fields of science and technology. This concept is known as biomimicry or bioinspiration, and it involves studying natural processes to develop new technologies, materials, and solutions. Nature often offers optimized solutions, which can inspire the development of new technologies, materials, and systems. As our aim is learning to fly, then the first choice for learning to fly is to mimic the best flyers in the nature and learn from them. When we're searching for the best flyers, we find the eagle as a fascinating flyer. It is known for its power and ability to fly at high altitudes. It flies even where no other bird can fly. Its ability to fly is very high. Although they have very long, large wings, and it takes a lot of energy to flap such large wings, they can achieve intuitive flights. In order to mimic the behavior of biological entities to evolve solutions for computational problems, huge variety of meta-heuristic optimization algorithms are developed. There are also several optimization algorithms inspired from eagles too. Here I give two recent studies for eagle optimization algorithms. However, developed algorithms cannot provide solution for the flight control yet. Flight dynamics are very complex and comprehensive dynamic computational methods are required to control, especially for the nonlinear modern control. So we need more advanced and intelligence computational methods. When we look for intelligent methods, we know that the world's most advanced computational processing unit is human brain. So we should work to imitate the computational process of brain. Now the question is, how can an air vehicle learn similar to a human being? Let's introduce an analogy between human and aerial vehicle. Learning to fly problem can be considered as learning to walk problem. A baby after 1 year old tries to walk and he learns to walk because he has a brain and neural networks inside. In case of our problem, if we consider the air vehicle as a baby, it needs also a brain. We can use CPUs, processors, or microprocessors as brains. Also, as biological neural networks, we have artificial neural networks. So we have similar computational mechanism between biological neural networks and artificial neural networks. Then the next step is to design artificial neural networks, ANNs, deploy them into CPUs, and install it in aerial vehicle. Classical ANNs are mostly used for classification, prediction, clustering problems. It was not possible for ANNs to deal with the complex continuous time dynamics of flight. Computing continuous time actions or complex dynamics was exceeded the capacity of classical ANNs. These tasks could be studied after the development of deep neural networks. Similar to classical ANNs, deep NNs also comprise neurons, but the amount of neurons used in deep NNs are much more than classical ANNs. With the advance of artificial intelligence, deep NNs become capable of handling flight control problem. Machine learning algorithms should be designed using these deep networks in order to make the aerial vehicle capable of learning. Machine learning falls in three different learning approaches. Supervised learning involves training a model on a labeled dataset. The model learns to map inputs to the correct outputs. It provides clear guidance but requires extensive labeled datasets. The second approach, unsupervised learning, deals with unlabeled data. It can handle scenarios when we have limited labeled data, but it might be harder to evaluate the learning. The last approach is reinforcement learning. Unlike supervised and unsupervised learning, reinforcement learning, RL, involves a sequential process where the agent learns through trial and error. RL involves learning through interactions with an environment and focuses on maximizing cumulative reward over time. Each type of learning approach has its strengths and weaknesses, but the RL is the most suitable choice for learning complex tasks such as navigation and manipulation. For learning tasks, the limitation of supervised learning approach is that training data sets may not accurately reflect the underlying flight dynamics. In general, supervised learning on its own is not suitable for interactive problems such as control. It has the risk of performing under the base controller, which is learned from. I mean, its performance would not be better than its supervisor. Both of supervised and unsupervised methodologies rely on existing data sets to try on. Both these methods need a data set that is even before the training starts. On the other hand, in reinforcement learning, there is no need for dataset before training starts. Therefore, we choose reinforcement learning to solve our control problem. As I said before, reinforcement learning, unlike supervised and unsupervised deep learning, does not require a pre-existing data set for the controller to learn. Reinforcement learning models start off in an unknown environment of which the controller only observes a presentation called the states. The controller interacts with the flight environment. It applies an action from the predefined action space. The controller starts off selecting actions randomly. The action will affect the environment in a certain way, and the controller will receive the new states and a reward or penalty value. This value determines how well the controller is doing at any given time. In this way, the controller will learn over time which action is best at what time, all its own. Since the decision of the controller entirely depends on the reward function, it's very important to define appropriate formula for the considered tasks. RL receives data from the flight environment at runtime and also interacts with it at runtime do actions. This interaction between controller and environment leads the controller to learn how to successfully achieve tasks in the environment. So this is a trial and error learning procedure. There is at no time given any direct instructions on what it should do, unlike the needed data sets for supervised learning. Instead of that, the controller receives a reward value and a state representation for each time it applies an action to the environment. The state is the only way the controller checks how well flying. Therefore, it's required to be determined carefully too. By using reinforcement learning, flight controller learns to fly by interacting with flight environment. Learning can be evaluated with physical real air vehicle and in real-life flight environment. While this may be possible, it will be very time-consuming and expensive. The controller, as I mentioned, starts off with zero knowledge of the task and learns the trial and error. Learning occurs through hundreds, thousands, sometimes millions of training trials. If a real physical aerial vehicle is used, as there is no way to accelerate the time, the training would take a very long time. Reinforcement learning is usually entirely based upon a trial and error learning approach. That means controllers act at random in the beginning of the training. If physical air vehicles are used for the training, they will misbehave, even crash during the early trials. Under this risk and fuel consumption of real aerial vehicles, real-world flights could become very pricey and dangerous. So, more convenient approach would be to conduct training in software. Flight dynamic models and flight simulators have accomplished near perfect flight physics simulation. Aerial vehicle models and flight simulators provides a valid, cheap, fast, and convenient alternative. Simulators allow for no-cost trainings, no physical crash. Accelerating the flight time is possible, meaning that, for example, we can complete 1 hour flight time in 10 minutes. Due to this advantage, we use models and simulators. However, we should design the simulations very carefully. After simulation calculations, we will deploy our algorithms to hardware and use the resultant intelligent controller in real-life flights. Transferring from simulation to the real world is very problematic without taking additional steps to increase realism in the simulator. These steps include realistic modeling of atmospheric disturbances, such as wind and turbulence, Another impactful step for successful transfer is the actuation delay. This delay occurs due to flight control system components, such as flight sensors and control surface actuators. To summarize, the differences between the simulation and real world that can be called as reality gap is very important, and it can be minimized by taking additional steps. I have also mentioned about that. Determining states and reward function is very important. Lastly, I should emphasize the importance of ANN's architecture. Usually, for ANN's architecture, it's important to define input, hidden, output layers, and transfer functions. However, additionally, for flight control problem, it's also important to incorporate memory functions in control policy. The memory function can make the controller able to infer the dynamics, not only at the current state, but also previous states. Therefore, a memory capacity of the state vector can be provided to give a sufficient history to infer the dynamics. In order to enhance this controller performance, for this purpose, recurrent NNs or convolution layers can be used in the ANN architecture. In order to design an intelligent controller, there are many different reinforcement learning algorithms available, and all of them have their differences. Some are inherently better studied to aerial vehicle control than others, but with the right modifications or adjustments, we can adapt these algorithms to work for our task. If you look at the picture, it becomes clear that proximal policy optimization and deep deterministic policy gradient have so far been the most commonly used algorithms. These two algorithms, among others, have gained a lot of attention due to their performance, and I recommend them for fixed wing air vehicle control too. I will give two implementation examples in reference for a model-free deep reinforcement learning PPO algorithm for fixed wing unmanned air vehicle is improved and compared with the most common control method PID. As you see, airspeed tracking performance of both PID and RL are better than remotely controlled UAV. And also the RL outperforms the PID. For the same air vehicle, in this figure, altitude tracking performance is depicted also. And here, 2D trajectory. So both altitude and 2D trajectory tracking performance of intelligent flight controller are higher than PID. In another research, deep deterministic policy gradient RL is used to control a UAV in order to track a target UAV. Three-dimensional trajectory of tracking control task in real-world flight is depicted. As it can be seen from the figure, the intelligent UAV precisely tracks the target. In the same research, in comparison with various control methods, the DDPG-based method outperforms the others in path tracking task under wind disturbances. As a conclusion, I can state that aerial vehicle can learn to fly through machine learning, particularly PPO, deep RL algorithms. We spent our effort to improve these algorithms at our Autonomous and Intelligent Systems Lab. There are also several challenges when working with these algorithms. We should ensure that learning algorithms do not lead to unsafe flight behaviors. Strict rules for testing and validation are required during real-life flights. Another challenge is the requirement of significant resources for training and real-time operation, which makes learning algorithms computationally intensive. It's also crucial to ensure that the acquired behaviors remain effective under various conditions and situations for successful implementation. Overall, the integration of learning approaches into flight control allows to improve flight capabilities. Based on these improvements, numerous studies, such as enhancing sustainability and energy efficiency of flights, can be conducted in the future. Thank you so much for listening. All questions are welcome.